Pine needles do not acidify your soil. What they actually do is refuse to lie flat, and 90 days underground shows why that matters more. Every single autumn, countless gardeners spend hours raking up fallen pine needles. You bag them, you haul them to the curb, and you wait for the city to take them away. You do this because someone once told you that pine needles are highly acidic and will ruin the ground beneath them. You were about to throw this away, thinking you were saving your garden from an invisible chemical threat. But when you look closely at what these needles actually do when they interact with moisture and soil particles, a different picture emerges. The physics here is settled. Structural geometry dictates how water moves through any porous medium. When you take a standard broadleaf, an oak leaf, a maple leaf, or an elm leaf, and it falls to the ground, it lies flat. Once rain hits that broadleaf, it acts like a shingle on a roof. A layer of wet leaves creates a laminar barrier. Water slides off the top, and whatever moisture does manage to get underneath is trapped, often leading to anaerobic conditions. But a pine needle is different. It is a rigid, elongated cylinder. When thousands of pine needles fall and accumulate, they do not stack flat. They crisscross. They interlock. They create a matrix of open-air spaces. This structural matrix is the foundation of proper soil hydrology. When rain falls on a bed of pine needles, the water does not sheet off. It percolates downward, guided by the cylindrical shape of the needles, drawing air down with it. You spend hours dragging heavy hoses across the yard in the middle of July because the ground dries out too fast. You lose that precious moisture to evaporation because the soil surface is exposed or covered in materials that break down into an impermeable crust. The pine needle, on the other hand, provides a physical shield that intercepts solar radiation while remaining permeable to liquid water and atmospheric gases. The structural shape of the needle is the key. Let us look at the form of the needle itself. Why does it not lie down and stick together like a maple leaf? The answer lies in its mechanical properties and its waxy coating. A fresh pine needle has a thick cuticle layer. This is an evolutionary adaptation designed to prevent moisture loss from the tree itself during harsh weather conditions. But once that needle falls to the ground, that same waxy coating serves a different mechanical purpose. It provides structural rigidity. When you drop a handful of pine needles onto the ground, they naturally form a chaotic, three-dimensional lattice. They bridge over each other. This lattice is mostly empty space. In soil mechanics, the ratio of empty space to solid material is called porosity. A high porosity layer on the surface of your soil acts as an extraordinary thermal insulator and moisture trap. Because the needles have that rigid, waxy cuticle, they resist immediate decomposition. A broadleaf might break down into a slimy paste within a few weeks of heavy rain. That paste seals the micropores at the soil surface. When the surface micropores are sealed, the soil beneath them can no longer exchange gases with the atmosphere. Oxygen cannot get in, and carbon dioxide cannot get out. This is a condition known as capping. Pine needles refuse to cap the soil. Their physical rigidity ensures that even under the weight of heavy rainfall or a layer of snow, the interstitial spaces between the needles remain open. The water flows through the macro channels created by the crisscrossing needles, gently infiltrating the soil surface without displacing the delicate soil aggregates. Chronology is where the true value of this structure becomes apparent. Let us trace the timeline of a pine needle layer over a period of 90 days. Day 1. The needles are fresh on the ground. The lattice is loose and springy. You have a highly aerated layer sitting on top of the mineral soil. Rain events pass through this layer instantly. The kinetic energy of the raindrops is absorbed by the interlocking cylinders, preventing soil compaction and erosion. If you were to look at a cross-section on day 1, you would see clean, dry air gaps between the needles. The moisture from the rain moves downward so efficiently that the uppermost layer of the matrix remains dry to the touch shortly after the storm passes. This dry top layer acts as a critical thermal break, keeping the deeper soil sheltered from the sun's direct radiant heat. Day 30. The matrix is still intact, but the internal dynamics have shifted. The bottom layer of needles, in direct contact with the moist soil, is beginning to soften slightly. However, the structural integrity of the cylinders remains firmly in place. The waxy cuticle is starting to degrade under the influence of soil fungi, but the needles have not collapsed. Fungal hyphae are beginning to bridge the gaps between the soil and the lowest needles. This fungal network acts like microscopic ropes, stabilizing the surface and pulling moisture up from the deeper soil layers during dry spells. A cross-section at this point reveals a gradient. Dry, rigid needles at the top, transitioning into a slightly darker, fungi-rich zone at the soil interface. The air channels remain unobstructed, allowing gas exchange to continue unimpeded. Day 60. The lower portion of the pine needle layer begins to yield, but it emphatically does not turn into a paste. Instead, it fractures into smaller cylindrical segments. These segments begin to integrate into the top few millimeters of the soil. Because they are still rigid pieces, they act like tiny pieces of rebar within the soil structure. They hold the soil aggregates apart, maintaining the critical macropores. The upper layer of needles is still intact, continuing to provide shade and reduce evaporative loss. The cross-section now shows a distinct blending zone where the organic material is physically propping open the mineral soil. Water applied to the surface navigates through the upper dry layer and then filters through this reinforced granular zone, distributing evenly without pooling. Day 90. A distinct structural channel system has fully formed. The needles at the soil interface have created a mature transition zone. This zone is rich in organic matter and fungal life, yet it remains highly porous. The structural rebar effect of the fragmented needles has permanently altered the top inch of the soil profile. When water is applied now, it does not just sit on the surface. It is rapidly drawn down through the structural channels established by the decaying needles. Published soil research on pine needle mulch finds that an additional 12 days of moisture retention compared to bare soil or soil covered with broadleaf mulch is routinely documented. That is almost 2 weeks of extra hydration without you lifting a finger or turning on a tap. The physical structure of the pine needle matrix has fundamentally altered the evaporation dynamics of the soil beneath it. To truly understand how this works, we need to address the widespread myth of acidity that causes so much of this valuable material to be discarded. The persistent belief that pine needles will turn your soil into a toxic, acidic wasteland is fundamentally flawed and lacks empirical backing in a typical garden setting. The myth originates from a misunderstanding of how the tree itself operates. Coniferous forests often have acidic soils, leading observers to wrongly conclude that the dropped needles are the primary cause of that acidity. In reality, the soil in those forests was likely acidic to begin with, which is why the conifers thrive there in the first place. When the needles fall, they do have a slightly acidic pH in their fresh, green state. However, this acidity is locked within the cellular structure of the needle. As the needles age, dry out, and turn brown, the state in which you rake them up, much of that initial acidity has already dissipated. Furthermore, published soil research reports that when these brown needles are placed on the soil surface, they do not release a flood of acid into the ground. Instead, they break down very slowly. As they decompose, the local microbiology, including bacteria and fungi, goes to work. These microorganisms process the organic matter, and in doing so, they buffer and neutralize any slight acidic compounds long before they can alter the bulk pH of the soil profile. Studies measuring the pH beneath heavy layers of pine needle mulch consistently show that the actual pH shift is minimal, often registering as less than 1/10 of a point on the pH scale. This microscopic variation is well within normal, healthy soil fluctuations. Rainwater itself is often slightly acidic, yet it does not destroy the garden. The fear of pine needle acidity is a chemical ghost story. Instead of focusing on imaginary chemical threats, focus on the mechanical reality shown in a cross-section of the soil profile at that 90-day mark. Imagine slicing straight down through the needle layer and into the earth below. At the very top, you have the coarse, interlocking lattice of intact pine needles. This is your atmospheric shield. It blocks the sun's rays, preventing the soil surface from heating up. It also acts as a windbreak at the micro level, stopping dry air from sweeping across the soil surface and wicking away moisture. Just below that, in the middle of the cross-section, you have the transition zone. Here, the needles are partially broken down. They are fragmented, and the spaces between them are filled with fungal mycelium. This zone is a moisture reservoir. The decaying organic matter holds water like a sponge, but because of the rigid needle fragments, it cannot compress. Then you reach the soil interface. This is the critical boundary. If you had used broadleaf mulch, this interface would likely be slick and compacted. But under the pine needles, the soil interface is crumbly and open. You can see the macropores extending downward into the mineral soil. The channels created by the physical presence of the needles allow the water to bypass the surface tension and move deep into the root zone. The physics here is settled. Water moves through soil based on pore size and connectivity. The pine needle matrix ensures that the largest pores, the macropores, remain open and connected directly to the atmosphere. When the sun beats down on the top layer, the heat cannot penetrate the air gaps in the matrix. The soil remains cool, and the moisture remains trapped in the micropores below. You have essentially built a one-way valve for water. It goes in easily during rain, but it cannot evaporate back out easily because the tortuous path through the needle matrix slows the vapor diffusion process. When you understand the physical properties of the materials in your garden, you stop throwing away the solutions to your biggest problems. If you want to keep exploring the physics of soil mechanics and how everyday objects dictate water movement, subscribe to the channel. In the next video, we are looking at the structural difference between natural cork and synthetic perlite, and why one of them lasts 3 years longer underground. The myth of acidity has driven gardeners to discard one of the most mechanically useful materials available. We have spent decades throwing away a free, structural mulch because of a misunderstanding of how organic matter breaks down. When you use pine needles as a surface mulch, you're utilizing their physical geometry to manage water. You're not changing the chemistry of your soil in any meaningful way. You're building an engineered surface layer that regulates temperature and hydrology. To apply this effectively, you should aim for a layer that is roughly 2 to 3 inches thick across the surface of your garden beds. Do not pack them down. Let them fall naturally to ensure the interlocking matrix maintains its maximum porosity. Keep the mulch an inch or two away from the immediate stems of your plants to allow for baseline air circulation, but cover the surrounding root zone generously. You can also use them beneath the surface. If you are preparing a new planting area and you have heavy, silty soil that tends to compact into a solid block, turning a layer of pine needles into the top few inches introduces immediate structural voids. Unlike soft compost that will eventually compress and disappear, the rigid needles will hold the soil aggregates apart for months, allowing roots to establish and water to penetrate. If you are working in a raised bed, layering pine needles at the very bottom before adding soil can create a drainage layer that prevents the lower regions from becoming waterlogged. By relying on the geometry of the material rather than chasing chemical ghosts, you save yourself the effort of hauling away good mulch, and you save your soil from rapid dehydration. The 12 extra days of moisture retention are not a matter of luck. They are a direct consequence of maintaining open-air channels at the soil interface. The pine needle matrix refuses to close those channels. The next time you see a pile of pine needles, recognize them for what they are: a highly engineered, slowly degrading physical matrix. They are not a chemical hazard. They are a mechanical asset. What is the most common advice you have heard about using pine needles in the garden, and have you ever tested it yourself? Let me know below,